what we have is this Raspberry Pi battery pack. This is the circuit on a breadboard. Basically, it's a very simple circuit. It's just got 5 components, 2 capacitors. The what looks like a transistor there is called a linear regulator, and on the other side here we've just got a LED, green LED, and a 5K resistor, so that we use very little current through that LED. So in comparison to the amount of current that this linear regulator will pass, it's about 300 times less. So we're able to keep that LED on all the while we're using the battery pack, and that's just really to let us know that it's still on when so you don't leave it on by accident. That's all that's for. Now the 2 capacitors on either side of the regulator, all they actually do is they lighten the load, so that if, for example, the Raspberry Pi starts doing something quite intensive and starts using a lot of current, then the voltage will drop on one side, and it means that this linear regulator will get different levels of loading. The 2 capacitors act as reservoirs, which just balance that out a bit, so that the regulator doesn't have to work too hard. So that's what the capacitor is for. You could actually use it without the capacitors, but using the capacitors means that the linear regulator will probably last a bit longer and be more reliable. So that's what they're for. This circuit is about as simple as they can get, but it's a good circuit, and there's a lot of useful knowledge you can gain out of this, which I'll go through now. What the linear regulator is supposed to do is make sure that the output voltage is fixed at a constant value. So for a Raspberry Pi, what we're after is 5 volts. In fact, the Raspberry Pi's got a sort of range. It can accept anything above 4.75 volts up to about 5.1, I think it is. So as long as you've got a fixed voltage within that range, then you'll be okay. So what we're after is about 4.85. I think that's what we've got on the output, which would be perfect. And if that can be regulated and kept at a constant value, then that's perfect. That's exactly what we want. So there you can see the LED's on now. So I've got the earth lead wired up. So we'll take the positive end, and we'll just hold that across and see what we've got. So I don't know if you can see that. We've got about 4.88. So that's perfect. That's exactly what we want. So that circuit does the job. Once you've got it working on the breadboard, the thing to do then is to build it onto a PCB board or a perf board, and then place it inside an enclosure. So what I use is obviously the tin cans. I'm using tin cans enclosures for all of these projects, which is just nice. They're very nice. They're just very low cost enclosures, and they do everything you need really. So you can drill these tin boxes really easily. I'll go through that on one of the videos on the website, where you can drill these holes. The tin's very soft, very easy to manipulate, and here you can see I've made a hole at one end for the actual USB socket. So quite nice, quite easy to do. So I'll show you that working at the end. What we'll do now is just go over exactly how these regulators work, so that you know. I mean, it's a lot better to build these things when you know where everything came from and why it does what it does. So what I'll do is just give you a general view first, and then we'll go into it in a bit more detail. So if we just look at the diagram here, we've got our N-loop batteries. Well, 6 of those times 1.2, we've got 7.2 volts. So actually these N-loop batteries actually go above 1.2, but they specify 1.2, but often they're about 1.25. So I think the voltage on there is more like 7.6 or something like that. So you've got quite a bit of leeway there. So you've got 7.2 volts on the input, and then this linear regulator, what it does is it will take whatever's on the input and it will reduce it to 5 volts, and it will keep it constant at 5 volts on the other end. This particular regulator will keep it at 5 volts. You can get different regulators for different voltages, but this LT1086, regulates anything that comes on the input to 5 volts, and it keeps it steady at 5 volts. Also on the circuit, I've just shown the 5k resistor with the LED. The reason I've used 5k, it's not a magic number, it's just as big a number as I could, as much of a resistance as I could before you couldn't see the LED, and that way you're not wasting any power through the LED. You could actually put like a 300 ohm resistor there, and you'd have a very bright LED. I mean, you could do that, but then your battery, you're going to use more of your battery. So the trick here is to use as big a resistor as you can, so that the LED is just visible, yeah, because you only need it to be visible to tell you that the thing's on. It doesn't have to be, you know, a power beam across the room or anything, so it's fine. So I got away with 5k there, and that works out like, I can't remember what it was, something like 0.1 of a milliamp or something, but it's a small amount of current. There's your two capacitors. Any values would do, really. I mean, any values between 1 and 20 microfarads, but 10 is what's in the data sheet, so I've used 210 microfarad, and they are tantalum, so they've got a plus and a minus. So you want, yeah, it's important that you use those type, either electrolytics or tantalums that are plus on one side, because you've got a lot of, what's happening in with the regulator is when the Raspberry Pi pulls more current and less current, and it might pull current when it's doing something CPU intensive, therefore there's going to be a lot of fluctuation. So you want to make sure that the capacitor is polarized, you know, it's got the right polarization, plus and minus. So we've got the LT1086. Now it's got a dropout voltage of 1.5 volts. That means within inside the minimum you can get out of this is a 1.5 volt drop. So, you know, if you had 6.5, that would be the best you could get. If you tried to run this below 6.5 volts, then you wouldn't get your 5 volts out. So that's what it means by 1.5. So that's the best you can get out of it. You know, the maximum efficiency is you're going to lose 1.5 volts. You're going to lose that as heat. But we're actually up to 7.2 volts. Now the interesting thing about a battery is you'll find that the start voltage is much higher than it generally will drop down quite a bit from that, and then you'll find that it's near enough 6.5 to 7 volts for most of its life. Yeah, this particular battery, that's, you can do the calculations, but that's the most efficient, because once you get close to your 1.5, that's the best you can do. And so this seems to be the best sort of compromise, is to go for 6 1.2 volt N-loop batteries. The N-loop because they got 1900 milliamp hours, so they last a long time. Right, so the power to dissipate using AA 1.2 volt batteries gives 6 times 1.2 volts, so that's 7.2 volts. So to regulate down to 5 volts, you need 7.2 minus 5, which gives you 2.2 volts. So to begin with, when we initially get this thing running, we're going to be wasting 2.2 volts at the very start. That's assuming an average current, you know, so in all the books that you read, in the everything that talks about the Raspberry Pi is generally talking about a maximum current draw of about 500 milliamps. So I've used that as our current draw here. So the power you could be looking at wasted from the 2.2 volts you're dropping there is 500 milliamps times 2.2, which is about 1.1 watts. Well, in the data sheet, these LT1086s can handle a lot more than 1.1 watts. So you could probably get away with not even using a heatsink for that. I've used a little heatsink in mine, but I probably didn't need to. But if you've got one and it's quite a small size and it's easy to get inside your tin, then go ahead, use one. No harm in using it. If it can fit inside the enclosure okay, or the tin in my case, then yeah, use one. So the circuit was built and tested. I've just shown you the circuit. Running a Raspberry Pi for 2 hours using 800 milliamp hour battery. Yeah, so I had some cheap 800 milliamp hour batteries, and I just wanted to give it a test. I didn't want to use my N loops to start with, so I used 800 milliamp hour batteries, and I found that that lasted for 2 hours. In fact, I didn't actually let the batteries run out. I stopped after 2 hours just because I ran out of time. I wanted to go somewhere. But then when I tried to start it up with the same batteries, they just then weren't. They couldn't, because when the Raspberry Pi initially boots, it draws a lot more current than when it's idling, when you're actually using it. So of course, after 2 hours, I tried to boot it and it wouldn't boot. Yeah, so that was quite good really, because it told me that the maximum you're going to get out of 800 milliamp hour batteries is 2 hours. But that's good. I mean, that's still good time, even on cheap batteries. But with the 1900 milliamp hours, so that's like, well over twice as big, getting close to 3 times as long lasting as these ones. But that doesn't equate to how long it will actually last. But I would say, having a guess, because I haven't done the experiment on this, but 1900 milliamp hour end loops, well, if 800 give 2 hours, and these are at least going to give 3 hours, possibly more. So 3 hours is just what I would want with this kind of Raspberry Pi battery pack. Because if you're going to have a Raspberry Pi battery pack, why would you have one anyway? Well, you're only going to have one if you're traveling, or you're at somewhere temporarily. I mean, it's not you're unlikely to be running your Raspberry Pi for a battery pack most of the time. Basically, that's just a quick sort of like discussion on what the Raspberry Pi battery pack is about. You look at this and you say, okay, I accept that 7.2 volts come in and it regulates it to 5 volts, but what actually is regulating a higher voltage to a fixed constant voltage? How is that done? That's interesting, because you could put 8 or 9 or 10 volts on that and it's still regulated at 5 volts. So something interesting is happening in here. And I don't know about you, but I will want to know why it does that. So I'm going to try and explain this to you. There's some concepts you might not have seen before, like op amps, how an op amp works and things like that. But it doesn't really matter. If you can get a rough feel, and then later on, as you get more into this, you can come back and have a look at this again, and then it'll make more sense. So just watch it through anyway, even if you don't fully understand what it all means to begin with. When you come back after studying some of this thing a bit more, or looking into it a bit more detail, it'll make more sense. But I'll try and keep it as simple as I can. So if we're looking at this LT1086, so what I'm going to do is, this circuit here is a typical representation of a regulator. So if you can understand this, you can understand all regulators basically, even though inside here is nothing like this. But this is kind of an abstraction of what a regulator does inside, and it's quite a good one, because they do use an op amp, and you will have most of these parts in here. This is called a pass transistor. This is an error amp. It's an op amplifier, and they call that an error amp. And this is a voltage reference, which often it will be a few diodes or something. But if you have a diode joined to the ground and a voltage above it, then what you can do with a diode is you can keep the voltage pretty much fixed at a particular value. But they probably don't use a diode. They probably use something quite sophisticated in there, so like some combination of transistors and current sources and God knows what else. But we can just look at that as a box and say that's a fixed voltage above there, and it doesn't differ. So that's the important thing with the how a regulator works, is this voltage reference box here. So we've got a load here. Let's just assume that this load could be the Raspberry Pi, for example, and it's now drawing less current than it was before. So it's suddenly found that it's got to do a lot more work, and the resistance, it could be the resistance has gone up, so there's less current flowing. If there's less current flowing through here, it means that the top of this is going to get closer to what the V in is, so you'll get a higher voltage on here. So I've said here, less current means V out will begin to increase. So we haven't then got a fixed voltage of 5 anymore. We might have like 5.2. Well, that's not what we want. We want a fixed voltage of 5. So how is this regulator going to bring that back down? Well, this is how it does it. So the Vref, as I said before, that's a fixed value. That's always solidly fixed. So the voltage at this point here, A, it's going to be higher than it was before, because obviously this voltage has got higher, this voltage will get higher too. So these have the same voltage above them. So if that one's high, that's the same voltage all the way along there. So that means this A has got a slightly higher voltage. Now if the point A is a slightly higher voltage, then now we look at an op-amp. Now an op-amp, there's some quickly a really sort of like 10-second description of an op-amp. An op-amp, first of all, what it wants to do is it will do whatever circuitry is inside the op-amp. It will do whatever it can to keep these two voltages at the same value when there's negative feedback. Now, negative feedback, what that means is the output is connected to what's called the inverting input. You see these signs here, minus and plus? They don't mean plus. They don't mean there's a bit of minus voltage or a bit of plus. They mean inverting and non-inverting. That's the way to look at those. Whenever you see an op-amp and you see these two symbols, don't think of plus and minus. Think of non-inverting, which means the plus, it's not inverting, and minus means inverting. So that's what that means. So an op-amp with negative feedback will always try and keep its inputs at the same voltage. So what does that mean? Well, it means if the plus voltage is at Vref, it means that the op-amp will do what it can. It will either increase or decrease to get that value there to the same value as Vref. So if we've got a high voltage here and it's higher than Vref, what's going to happen? So with a high voltage on here, that's going to come out lower. So you've got a lower voltage here. Now with a lower voltage across this transistor, you know that at the base of a transistor, if you drop the voltage at the base, then you're going to allow less current through the transistor. So if you're allowing less current through the transistor, you're reducing this voltage at this point. So what we've actually done is we've reduced the voltage at VL. Now you can look at it the other way around. Say that there's a lot of current being drawn through the load now. That means the voltage has dropped. So now we're below 5 volts. Well, that means that the A has dropped in voltage. Now if the inverting input is dropping, the voltage here at C will increase, and when it goes to the base of the transistor, we've got now an increase in voltage. That means we're going to allow more current through. If we allow more current through, then this voltage is going to increase. So then we've brought the voltage back up to 5. So that's how regulation works. It's basically all about the behavior of this op-amp. So that's really what's going on inside here. The other nice thing about this, if you get into this voltage divider and how to analyze an op-amp, you can end up with this nice little equation. Now this equation is really good. It says the voltage out equals the Vref voltage, which is this one, brackets 1 add R1 over R2. Notice in this formula, Vin is not mentioned. It doesn't come into this formula. The only things that are mentioned in this formula is this fixed Vref, which in this case is about 1.5 here, and these two resistors are fixed. Now that's inside here, yeah? So you can always work out your voltage out if you know these values, yeah? In this case, all of that's inside, and we're just getting a 5 volt out, so we don't have privy to any of this. But there are other voltage regulators where we can control all this. So I'm going to just boot this up, and then I'm going to set up VNC Viewer on my Nexus 7. It's all in a nice little box here, so you can't really see it, but the Pi's in there. So let's get our battery pack, and this is our linear regulator. I've put it in a tin box. It's all been soldered up, everything's done, and that's just, there's the green light. So the green light's on, and we should start seeing some activity on this. I don't know if you can see that those red lights, hopefully. So you can see it booting. Eventually that red light will just stay fixed, and then I can try and connect again with my Nexus 7. I think that's kind of booted now, so let's give it another go with the Nexus 7 and see if we can get in. So I'll just try that again. Okay, yeah, well, it's given me the prompt, so it's obviously done it. So now I can just type in my password. and I just hit OK. There you go, we're in. There it is. So we've got a headless Raspberry Pi there, and we're in. We can. So there's the Raspberry Pi. It's working, and it's not on the mains. It's just using these little batteries here. Like I said before, I used them some very cheap 800 milliamp hours. These ones, I don't know if that company's familiar to you, but 6 of those lasted 2 hours. So these ones are 1900 milliamp hour. So I should get 3 hours out of those, possibly more with a bit of luck. But there you go. That's the project, and that's what you'll get. You'll get these 5 components and a little board to solder them on, and your tin. And it's a great little project just to get you going.